Howdy folks! Today's episode is going to be focused on the N64's weird controller, as well as building on the basic game loop that we designed last episode. So sometime after last episode, my TV decided to be a little shocking. The part that's arcing is called the flyback transformer, and it's a pretty vital component, so it behaving like that is a little bit annoying. Unfortunately, flyback transformers aren't really a thing anymore because CRTs are largely obsolete technology. But fortunately, I was able to get it working using hot glue. Now the TV works perfectly. Observe. I actually got really lucky and I found a website that was selling this exact model of a flyback transformer, so replacing this old one was actually pretty easy. Would it have been easier to have just bought a new TV? Sure, but where's the fun in that? So yeah, my TV is now in working order. Hooray! Now the N64's controller is somewhat infamous for being a little weird. And I'm not referring to how you hold it, that's really obvious. You hold it like this if you want to use the D-pad, and you hold it like this if you want to use the control stick. I'm actually referring to the stick and how it's known for wearing out really easily. This is actually going to affect quite a few things in our game, so we're going to have to deal with that. Now I can show you why this happens, but instead of tearing this one apart, through the magic of owning two of them, I have an already taken apart one right here. The stick's data is stored as 16 bits. 8 bits for the X value and 8 bits for the Y. You can think of it as a two-dimensional Cartesian plane. When the stick is centered, it's at 0, 0. And obviously pushing it to the left and to the right changes its X value, while pushing it up and down changes its Y. Due to the shape of the stick's shell, unlike a modern day controller which will make circles, the N64 stick will form an octagon, with maximum values typically following somewhere in the range of this diagram for original controllers. As you can see, this stick is a little bit loose, and that's because this entire enclosure is plastic, and these are all plastic parts, and you have plastic rubbing on plastic. And so there's a little bowl inside of the stick which will wear out over time, and now the stick will no longer sit flush. So let's take this one apart and we'll understand a bit better what's going on. And so here's the bowl, and you can see all of this rubbed off plastic that this is constantly working against. And there's these extra gears here where this little stick is supposed to sit in. And because these are also plastic, they get worn out, and now the stick can no longer sit here flush. There's a little bit of give. Luckily, Nintendo learned from this mistake and never designed controllers with sticks that fail easily. In case you're curious, modern game controllers don't have this problem because they use a different potentiometer design. This doesn't actually involve any parts touching one another. I'm not saying that this design is flawless, but they do tend to last a lot longer, and they are much easier to swap out. Another thing that developers back then didn't need to worry about, but they do now, is that we have a lot of third-party controllers. And so even different stick replacements will have different designs, and this won't be too much of a problem if it weren't for the fact that they don't usually respect the joystick ranges from the original sticks. Now, the fact that games expected the stick to fall in a certain range can lead to some interesting quirks, or basically really annoying controls in some situations. It's my controversial belief that games should try to be as accessible as possible, and so finding a way to deal with all this different hardware is a little important. Furthermore, the N64's controller also has accessory support, letting you have external saves, or interface with Game Boy cartridges, or vibrate. Of these accessories, the only one that I'm really interested in supporting is the Rumble Pack. Now, saves on the N64 are typically stored in the cartridge itself, with the most common being EEPROM of 4 kilobits, which is equivalent to 500 bytes. The controller pack, on the other hand, would allow a single game save to occupy a bit under 31 kilobytes of memory, but most games would only end up taking 2 kilobytes, so you could save multiple games into one pack. Unfortunately, some games, like Mystical Ninja 2... Alright, let me just... Okay. ...did not have an EEPROM in the cartridge, so a controller pack was required for saving. As a kid, this meant that I basically had to beat the game in one sitting since I didn't own one. So to me, it's a little important that the game that I'm working on not require a controller pack. Support in order to allow people to transfer saves could be added in the future, but not a priority at all. Now, one interesting tidbit about the N64's controller is how it handles the stick calibration. When you boot the console, it assumes that the stick's current position is the neutral center position. So if I decide to push the stick to the right and I boot the console, now it assumes that this is the center 0, 0. This might seem really weird, but this is how game controllers work nowadays. You can even test this in your own home console. So right now it assumes that this here is the center 0, 0. So if I let go, now it's moving to the left. And it's basically stuck like this for the rest of the game. But the thing that's unique about the N64's controller is that you can calibrate the stick at any time by pressing R, L, and start. And now the stick should be behaving like it's supposed to. Nintendo made it a specific requirement in their game submission form that developers avoid any situation where the player would end up pressing these buttons at the same time. Now, developers might not have taken into account that a player can do that at any time. And so there's some interesting speedrunning hacks that you can do in some games. Disco Ninja is a good example. Okay, so here's a pole, right? And I'm going to get on the pole and spin, and now I'm pushing up on the stick. And, ooh, that was a bit more diagonal. There we go. You can get more or less an idea of how high the character can go. But now let's do something interesting. Let's get off the stick. Let's recalibrate so that the bottom is the new center. And now if I jump on the stick and I spin and now I push up, yeah, that's some height. Okay, so now that we know everything about the controller on the inside, let's actually talk about programming the controller for our game. We've discussed previously that the game loop looks like this. We'll want to initialize the controller once before the loop, and then poll for controller changes as soon as possible, preferably in a separate thread. So it would make sense to read our controller before updating the level, because we'll want our characters to react instantly to our input. The issue, however, is that controller reading isn't instant. In fact, in a worst case scenario, it can take up to 2 milliseconds. This could mean that the input could suddenly change while the game is still processing our character's logic. So it's actually better for us to poll for input after the fact, as the render task is not dependent on the input values. Yes, this means that the character input will always be 1 frame behind, but you will not notice this in practice. I've said earlier in this episode that the control stick data is stored as 2 8-bit values, but what about the buttons? The N64's controller has 14 buttons, so the console gives you a 16-bit value where each bit tells you whether the button is currently held down. This is known as a bit field, and it's a pretty common way of storing lots of true and false values together. If we want to know stuff such as whether the button was pressed or whether it was released, instead of just simply knowing that the button is currently held down, then we have to keep a copy of the previous controller data as well, so that we can then compare the current data to. That's basically all there is to it. But as I have previously highlighted, it's not good enough for me. I want users to be able to completely customize their controls, which very few games on the system provide support for, and most which do only have some sort of fixed set of control schemes instead of letting you pick each button for yourself, which is much more common nowadays because it turns out accessibility is really important. My approach to this was, instead of thinking about buttons, thinking about actions. Because the entire controller state can be stored as 16 bits, we can create a bit mask for each associated action. And then to check if the user performed the action, we simply take the controller state and we apply the mask to it. If the resulting value is non-zero, then that means that the action is being performed. One of the benefits of using a bit mask is that we can very easily associate multiple buttons with a single action. Modern games instead only usually let you at most associate 2 buttons with a single action. Of course, this is also because modern game controls are way more complicated than just 16 buttons which can be represented with a single on and off bit. Dealing with a control stick is a little bit trickier. Modern game consoles give you the ability to customize the dead zone, which is a range of values which the game will typically ignore. This is useful for fighting what is called joystick drift, which is when worn out sticks are unable to return back to 0-0 perfectly, and thus the game thinks that you are still moving the character. The N64's controller is a bit weirder though, because not only is the controller unable to make circles, the ranges are different in every point of the octagon. Well, I would call it an octagon, but that doesn't even ring true for third-party controllers. My solution to this is to instead allow users to completely customize their stick shape. The outside shape is the maximum value. So if the stick goes over it, it will be treated as if it was on the edge. Similarly, any values inside the dead zone will be treated as 0. By default, my game will assume original stick values, but the code basically lets the user move each point in the stick octagon forwards and backwards, giving you control over their maximum value as well as their dead zone. So no matter how weird your stick is, my game will let you support it. The way that this works is by projecting a line from the center to the stick coordinate and calculating its distance from the inner shape to the outer shape as a percentage. However, this alone would be weird, because if you think of a unit circle on the Cartesian plane, the corners don't represent 100%, otherwise the circle would look like a square. So we also need to calculate the angle of the projected line and multiply the final range by sine and cosine to fit it back into a circle. Another interesting thing that the N64 supports, but not many games deal with properly, is controller hot swapping. The N64 has 4 controller ports, but most games only treat controller port 1 as player 1, port 2 as player 2, etc, etc. Some games will only initialize the controllers at the start of the game, meaning if you plug in player 2 after the fact, the game won't detect the new controller until you restart. My implementation of the controller code basically checks the ports from left to right, assigning a new player number to the first non-empty port it finds. If a port is unplugged, it will assume that the next new leftmost plugged-in controller is the old player. Of course, if the console's reset, then the leftmost port will become the new player 1. I seriously doubt people are going to be hot swapping their controllers during gameplay, but it was something that was relatively easy to implement and doesn't hurt to have. The last thing I implemented worth mentioning is support for rumble. This is as simple as checking if the rumble pack initialization function doesn't return any errors. The tricky part is that the N64 doesn't provide a way to adjust the rumble. It's either on or off. So if I want the rumble to have different levels of intensity, I have to turn it on and off in a specific frequency. Since the controller code is running in a separate thread, this is done through timers, which will send a message to the controller thread when it's time to handle the new rumble state. My rumble code is abstracted as trauma. You basically apply trauma as a percentage, and it will naturally decay to 0. And of course, the trauma is additive, so you can keep stacking it on to make it more intense. One fun bug regarding the rumble pack is that it's not enough to call the stop rumbling function once. Nintendo recommends calling it at least 3 times, and even that might not fully stop the rumble. This is because wear and tear on the controller's accessory port causes the contacts on the rumble to not sit flush, so it's possible that the motor does not receive the signal to stop. As usual, the code for all of this is available in the description. If you're a retro games enthusiast, and let's face it, if you're watching this series, that's incredibly likely, then you've probably run into this issue where you've tried to run old games on new hardware and noticed that the games are running a bit faster than they're supposed to. This is because back then, developers were only expecting their games to run on very specific hardware. And right now, our version of the ROM will run into that same problem, because there's differences between N64s. Specifically, the American N64s will run faster than the PAL European N64s because their processor is faster. Since in NTSC you're pushing 30 frames a second, you need to do it faster than the PAL consoles that are doing 25 frames a second. I suspect that this is one of the main reasons that games take forever to come out in Europe at the time, since developers likely targeted American hardware first and then had to deal with the consequences of trying to get them running on European consoles later. The current design of our game loop is what is known as frame rate dependent loop, because the game's speed will be affected by how fast the game is able to push out frames. This means that lag will physically slow down the simulation of our game. So let's talk about how to achieve frame rate independence and the consequences we're going to have to deal with. Imagine our game world is represented by a 2D Cartesian plane. We have a moving object, which will be represented by this rectangle and a wall to block it. The position of the rectangle on this plane is represented by a single coordinate at its center. So to move it, we simply increment its x value every time the update function is called. If the rectangle overlaps the wall, aka a collision happens, its x value is set to place the rectangle before the wall. Right now we are frame rate dependent because the update function will be called more times if the frame rate is higher, making the rectangle move faster. Thus, its speed is dependent on the frame rate. The obvious solution to solving this is by measuring the time it took to render the previous frame, and then instead of incrementing x by a static value, we multiply that static value by the frame time. Looks like we solved the problem really easily, right? I mean, if the frame rate is faster, then the rectangle will move by smaller increments, while large gaps in the frame rate will cause it to move by larger increments. Well, the latter point is precisely the problem, because if for some reason the game lags for a sufficiently long time, the speed of the rectangle will be so large that the rectangle's next coordinate is far past the wall, causing it to quantum tunnel through the wall. There are some solutions to this, like we could project a line from the previous position of the rectangle and see if it intersects the wall. Oh, but that won't work in this scenario where the rectangle definitely should have collided but didn't. Well, we could project the entire shape. I guess that will work, but you have to do that for all the objects in the game, which will be very heavy. The big issue with this system is that you have variable time, so you will get variable results. For instance, consider the situation where every time the update function is called, we want to double a value. If we simulate this for a specific time frame, but with different frame rates, the final value will be different, even though we took into account the frame time. This can become a bit annoying to debug physics issues. For games, it is generally a good idea to keep the physics simulation in a fixed, discrete time step. But that runs counter to wanting the frame rate to be variable. So the answer to this is to keep the simulation happening at discrete intervals, but separate from the frame rate. Let's call each time step a tick, and call the amount of ticks per second the tick rate. Now, it would be in our best interest to have the tick rate be the same as the frame rate, or a higher value like double the frame rate. But you might have noticed a small problem, which is the fact that if the frame rate doesn't fall into a multiple of the tick rate, there will be time variation between render updates and scene updates, resulting in jittery looking movement. So how do we solve this? The answer is to lie to the player by showing everything on the screen a little bit behind of what actually happened, as opposed to what is really happening. By keeping the frame a little bit behind the ticks, we can store the state of the world in the current tick and the previous tick. And then we can linearly interpolate based on when the frame was generated in the subtick. Like this, we can have a deterministic world simulation with a variable frame rate. You might say, wait, doesn't that mean that what I see on the screen isn't really what's happening in the world simulation and is technically a few subticks behind reality? Well, let me let you in on a little secret. Modern games, especially multiplayer games, already do this all the time, and you probably haven't noticed. They're constantly lying to you about time. Now, this solution obviously isn't perfect. One easy problem example would be something like a projectile going over a wall. If a rectangle follows the projectile path perfectly, we can see that it never collides with the wall. But since we are taking discrete time steps, we only see discrete moments in time. We could end up in a situation where the tick interpolation causes the rectangle to look like it collided with the wall, when in reality it really didn't. We can fix this with a more accurate type of interpolation, at the obvious expense of making the processing a lot heavier, but we still won't be able to fix everything for a bunch of reasons that getting into this in this video would turn it into a multi-hour long lecture about game engine design. So how do you actually implement a game loop which works for constant time but variable frame rate? I find the best way to go about it is the frame time produces time, which our update function consumes in discrete steps. We can create a variable called the accumulator, as well as a variable which stored the time in which the previous frame was rendered. At the start of the loop, we subtracted 2 time steps to get the time it took for the previous frame to render, which we'll call frame time, and then we'll add this value onto the accumulator. Whenever the time inside the accumulator exceeds the tick rate time, we can consume a single tick's worth of time and simulate the world accordingly. Of course, since we are consuming discrete time steps until the accumulator cannot give us enough for a tick, this means that there will be scenarios where we might call the update function multiple times in a frame, which is perfectly fine. Clever folks might have noticed a small problem with this approach. What if the frame rate slows down so much that the time produced by the renderer is so high, resulting in the update loop requiring a lot of updates in a single frame, which in turn slows down the frame rate, which then produces a larger amount of updates in a single frame forever and forever. The only way to solve this is to put a cap on how many updates we can have in a single frame. This of course means that at a sufficiently slow frame rate, the game simulation will actually slow down. But that is unavoidable in this scenario unless we no longer update in discrete steps, which was the whole point of the system. To perform the interpolation between ticks, we make use of the fact that the accumulator still has unconsumed time in it. By dividing the accumulator by the time of a tick, we can get the subtick value, which we can use during rendering to calculate the position of objects given the frame's time between ticks. This of course requires that we store the position of objects both for the current tick and the previous tick. If we want objects to teleport, this interpolation at really high frame rates might cause it to appear as if the objects moved really fast between 2 points as opposed to just teleporting. The only solution here is to disable the interpolation on this object for the specific frame. You might be curious, what is the best value for the tick rate? Too low of a tick rate with a really high frame rate will result in stuff like parabolic motion looking off because of the linear interpolation. Too high of a tick rate might slow down the rendering significantly. I don't know how to answer that. I will have to keep testing values until I find a nice balance. For instance, Doom, which came out 3 years before the N64, uses a tick rate of 35. For the time being, I have it set to 50, but I don't know if this is too much for the system to handle until I have more meat on the game. And here is that code in action. Since this is a PAL console, it's running at 50 frames with 50 ticks. You should see just how smooth this is. If I press the button in the back of the cartridge, then I'll introduce lag. And you see that despite there being lag, that the simulation stays constant. The movement of the rectangle respects the time that it took to get there. To really hammer down just how cool this interpolation system is, here's the exact same ROM, but this time I'm gonna set it to run at 15 ticks instead of 50. You can't even tell the difference. As usual, code is in the description. The last thing I want to cover in this episode is to take our basic game loop and to design a level system around it. This will allow us later down the line to split our code into multiple chunks and load them into memory only when they're necessary. Now, I'm not going to do the memory management part of it yet in this episode because it's already complicated enough, but we're just going to modify our game loop to be able to jump between levels. This should be relatively easy. Basically, each level is split into its own set of functions. For each level, we'll have a start, update, and end function. For drawing the level, we'll want to make it a list of drawing functions, because we might want to have multiple render tasks per frame later down the line. We'll have to make a second loop for our main thread, and make the innermost loop run until the level is requested to change through a changeLevel function. When the game starts, it will call the level start function, which will initialize everything that is necessary. Then it will enter our game loop with the tick system we wrote previously. Here, it will update the level and then make render requests for the graphics thread. Once the level change function is called, it will break out of the loop, and the end function will both clean up any memory I might have used, we'll discuss this in another episode, but also tell the engine to switch the level functions it's going to use to the new levels. When the loop restarts, it will now use the level initialization function for the other level. Yeah, guess that's really all there is to it. So I guess I can just end the episode. So when I was writing out this series, I had more or less an idea of what I was going to cover in each episode. And what I'm covering right now is something that I was only expecting to have to do later, but I got really annoyed, so I just spent 2 days working on this. You see, back in the old days, it was pretty common to have large code projects with hundreds of files all in one folder, which, while very messy to navigate, simplified the compiler's job a lot, since it just had to compile everything that was in that folder. Obviously, I don't want my project to look like this. I'd rather structure it with folders and have the compiler properly detect changes to code and recompile things that depend on those changes and all that fancy stuff. Any C programmer worth his salt would probably know how to set up a project to basically fulfill those requirements. Unfortunately, the SDK I use is over 25 years old and its age shows. Good lord, does it show. I got so fed up trying to get those two basic requirements working that I just ended up saying, screw it, I'm designing my own build system with blackjack and hookers. And that's basically what I did. I wrote in C++ a new tool that basically takes my code and just compiles it into a ROM in the way that I wanted. I've also gone ahead and taken the repository on GitHub and added Azure pipelines. So whenever I submit any changes to the project, some computer somewhere in the world owned by Microsoft will basically download my repository and compile it and then publish the things so that people can use the tools. A common question I get is, we have quite a few alternatives for SDKs, so why do you stick to something so old? And the reason is because what I'm using is very much battle tested. I don't have to worry about my project's tools misbehaving as I'm developing. Somewhat. Basically, when I'm working on a project of this scope, I just don't want to take any chances, so I just want to work with something that I know works. Well, now we covered everything that I wanted to in this episode. Next episode, we're going to be covering sound and music on the N64. And that will require that we make some changes to our scheduler, which hopefully won't be too bad. Well, as usual, thanks for sticking around and following this project, and hopefully I'll see you in a few months.